Introduction to Equilibrium. Let's do some review of some vocabulary we've used in previous sections. We talked about chemical kinetics, and we know that chemical kinetics explains how chemical reactions take place, and it deals with how some of the factors that affect the reaction's speed. We also talked about the term equilibrium, and we know that a system is at equilibrium when the rate of opposing forces are equal. Remember that we talked about equilibrium when we dealt with vapor pressures and the dissolving process. We said for vapor pressures, when the rate of evaporation equals the rate of condensation, the system was at equilibrium. Or when we talk about the dissolving process, when we have a saturated solution and the rate of dissolving equals the rate of precipitating, our system is at equilibrium. Now, we know that some chemical reactions go to completion, and actually all the chemical reactions we've talked about so far, we've assumed that those reactions have gone to completion. And what we mean by that is one or more of the reactants run out, and the reaction stops once we run out of at least one of the reactants. But many reactions behave in a different way. Let's look at this as an example. Let's say we've got reactants A and B forming products C and D. The capital letters stand for whatever the reactants and the products are, and the lowercase letters stand for the coefficients in the balanced equation. At first, we don't have any C or D. All we have is A and B. They start to react together, and C and D are starting to be formed. But after a while, once we start to produce C and D may start to react to reform A and B. So we've got C and D producing A and B. These reactions proceed until the two rates are equal. And at that point, we have what's called a chemical equilibrium. So we've got A plus B producing C plus D, which is at a high rate initially, and its rate starts to go down as the concentration of A and B go down. As C and D start to be produced and their concentrations increase, the rate of reaction for C and D goes up, and we start to reproduce A and B, and when the rate of the forward reaction equals the rate of the reverse reaction, we have chemical equilibrium. So chemical equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. Now, when we get to chemical equilibrium, the reaction doesn't stop. The rate of the forward reaction and the rate of the reverse reaction are equal, but those two reactions are still proceeding. At the microscopic level, there's a lot going on, even though it doesn't look like anything's going on at the macroscopic level. So because the rates are the same, the net change in concentration for A, B, C, and D become a constant. And we say that chemical equilibrium is a dynamic equilibrium because when we look at it, it looks like nothing's going on, but at the molecular level, it's very dynamic. And the way we would write that is A plus B produces C plus D, and C plus D produces A plus B, so we've got that arrow going in two directions when we look at a system that's at equilibrium. It's important to remember, though, that at equilibrium, the concentrations of the chemicals becomes a constant, but they're not necessarily equal. So A and B and C and D will have the same concentrations once we're at equilibrium, but they're not necessarily all equal to each other. Now let's talk about law of mass action. And law of mass action is a general description of an equilibrium condition. So let's say we've got A plus B producing C plus D. The lowercase j, k, n, and m are the coefficients in the balanced equation. And notice that the arrow is going in two directions, which tells us we're looking at a reversible reaction. And when the system's at equilibrium, the rate at which A plus B produces C plus D is equal to the rate at which C plus D produces A plus B. Now the law of mass action that we would write for this particular equilibrium system looks something like this. We've got a capital K equals the concentration of C to the N times D to the M over the concentration of A to the J times the concentration of B to the K. Notice that the products are in the numerator and the reactants are in the denominator. We're dealing with concentrations, and we're going to raise the concentration of each of those substances by the coefficient in the balanced equation. Now the brackets indicate the concentrations when the system are at equilibrium, and we refer to K as the equilibrium constant. Now let's talk about this process called the Haber process. And the Haber process was a very important process because it was used to produce fertilizers. Fertilizer generation from ammonia was produced by this Haber process, and it's estimated to be responsible for sustaining 1/3 of the Earth's population. It's estimated that half of the protein within human beings is made of nitrogen that was originally fixed by this Haber process. So it's a really important process, and it's used a lot in equilibrium examples. So what we want to do is we've got this balanced equation. We want to write the law of mass action expression for this reaction. Sometimes it's just referred to as the equilibrium expression. And then we're given the concentrations of reactants and products at equilibrium, and we're asked to calculate K. All right, so we'll start with the law of mass action. So we've got K equals. We're going to put the products in the numerator and the reactants in the denominator. So we've got the concentration of ammonia. We'll raise it to the power of the coefficient in the balanced equation, so we'll put it 2. We'll put the reactants in the denominator. So the concentration of nitrogen, and the coefficient is a 1, times the concentration of hydrogen, and the coefficient is a 3. So there's our law of mass action expression, or our equilibrium expression. Now we're going to plug in the equilibrium concentrations that were given. So we've got 3.1 times 10 to the minus 2, and we're going to have to square that number, over 8.5 times 10 to the minus 1 times 3.1 times 10 to the minus 3, and we're going to need to cube that number. Now since all the given numbers have 2 significant digits in it, we'll round our answer to 2 significant digits, and we're going to get 38,000 for our answer. And that's a pretty big number, which represents the fact that the equilibrium is established far to the right in this reaction. In other words, we're going to have a lot of product compared to reactant when the system's at equilibrium. Now, some important things that we should be aware of. If we were to take a reaction and reverse it, and we wanted to write the K expression and calculate the K value for the reverse reaction, we could plug in all the numbers and get the answer, or we could realize that we're just switching the reactants and the products, so we're taking the reciprocal of the original K value, and that would give us the K for the reverse reaction. Now sometimes it might be necessary to take a reaction and multiply it by a factor. If we wanted to calculate the K for the new reaction with the multiplied factor, we could again write out the new K expression and plug in the numbers and get an answer, but the new K value would equal K raised to the factor we multiplied the reaction by. Might make it a little bit easier. Now, when we talk about units for K, it depends on what the powers are for the concentrations of the reactants and the products, so it's going to vary. And pretty much all the time, we're not even going to write a unit for K in our problems. And a couple things that we should just remember. K values are always the same at specific temperatures, regardless of the amount of reactants that we start initially with. K is a constant. And although K is always the same, the equilibrium concentrations will not always be the same. It's a ratio of those concentrations we're dealing with when we talk about K.